This video gives an introduction to unsupervised learning with a simple example in C++. Billy will first explain to us what machine learning is and how unsupervised learning works.
Machine learning is generally classified into three paradigms: supervised learning, unsupervised learning, and reinforcement learning. In the previous few videos, we explored supervised and reinforcement learning. In supervised learning, the machine learns from a training set of labeled examples. For instance, as shown in this diagram, the model is trained to classify inputs as triangles, circles, rectangles, or hexagons based on labeled data. However, this kind of learning isn't suitable when the goal is to learn from interaction rather than from labeled data. That's where reinforcement learning, RL, comes in. Interestingly, RL is also considered a form of unsupervised learning. There are no explicit labels or targets provided. Instead, an agent learns through its own experiences, interacting with an environment to achieve a specific goal. The agent is rewarded when it takes actions that lead to good outcomes. It is penalized when it makes poor decisions. This is similar to how animals, or even babies, learn through trial and error. In this video, we explore the third paradigm, unsupervised learning, which is a type of machine learning where the model is given unlabeled data, and its goal is to discover hidden patterns or structure within that data without being told what the correct output is. In contrast to supervised learning, where each example comes with an associated label, such as a figure labeled triangle or circle, unsupervised learning works only with input data. No correct answers are provided. Here are some examples of unsupervised learning in action. 1. Clustering. Groups similar data points together based on their characteristics, such as customer segmentation in marketing, where customers with similar purchasing behaviors are grouped together. 2. Anomaly detection. Identifies unusual patterns that do not conform to expected behavior. For example, it could detect fraudulent transactions based on deviations from normal spending patterns. 3. Dimensionality reduction. Reduces the number of features or variables in a dataset, while preserving its essential structure, often used to simplify data analysis. 4. Association rule mining. Discovers relationships or patterns between variables in a dataset, such as identifying items that are frequently purchased together. 5. Topic modeling. Discovers the underlying topics or themes in a collection of documents. As shown in this diagram, unsupervised learning identified topics from the raw text data. 6. Image and video analysis. Analyzes visual data to identify objects, scenes, or patterns. 7. Recommendation systems. Predict items a user might be interested in based on their past behavior and the behaviors of other users, such as recommending a video watched by a user to another user who has watched similar videos. 8. Medical diagnosis. Identifies clusters of patients with similar symptoms to aid in early diagnosis and treatment planning. In summary, unsupervised learning finds patterns or structure in unlabeled data. It allows AI to explore data and discover insights without being explicitly told what to find. It's commonly used for clustering, dimensionality reduction, and anomaly detection. The model learns from the data itself, not from predefined answers. Below we explore a simple example of unsupervised learning, k-means clustering. K-means clustering is an unsupervised learning algorithm that groups data points into clusters based on their similarity. Unlike supervised learning, it identifies patterns in the data without relying on labeled examples. For instance, suppose we have customer data with features such as age, income, shopping frequency, but no labels are provided. We can apply k-means clustering to group these customers into, say, 3 clusters. Cluster 1, young and budget conscious. Cluster 2, middle-aged professionals. Cluster 3, high-income frequent shoppers. Each cluster can be used to tailor marketing strategies, and all of this is done without labeled training data. The algorithm works iteratively as follows. 1. Randomly pick k central points, called centroids or means. 2. Each data point is assigned to the closest centroid, thus obtain k clusters. 3. Update the centroids by finding the average position of each cluster. 4. Iterate the process for a number of times until the clusters become stable. This method is widely used for tasks like customer segmentation, image compression, and anomaly detection. Here is a simple C++ implementation of k-means clustering. This is a header file, k-means.h, which defines the point struct that specifies the 2D coordinates of a point and the cluster it belongs to. K-means is the function that clusters the points and is in the file k-means.cpp. The function distance calculates the distance from a point P to a centroid C. The function k-means clusters 2D points stored in the vector points and returns the centroids via the vector centroids. Iterations is an input parameter. The function iterates the clustering steps iterations number of times. Within this loop, it classifies a point to a cluster by calculating its distances to the cluster centers. The one with the shortest distance is the cluster it belongs to. This code segment recalculates the cluster centers, or centroids. This is a testing routine, saved in the file testmeans.cpp. It creates a vector of 2D random points as testing data. It sets k to be 3 and iterations to be 20. It randomly initializes centroids from the points in the vector. It then calls k-means to do the clustering and print out the results. Here are some sample outputs from the program. The outputs may vary in each execution, depending on the initial random choice of centroids. We'll copy, compile, and run the program later. For now, let's discuss a simple graphical interface for it, which could provide deeper insight into the algorithm. This program test kmeansg.cpp tests the k-means function using a graphical interface. The function do k-means dynamically sets k to 3 or 4 based on the number of data points. It initializes centroids randomly from the dataset and then calls k-means to perform clustering. The final cluster centers are returned in the vector centroids. It then prints out the results. The following code provides a basic graphical interface using the OpenGL library, with a window size of 600 × 500 pixels. The main function does the typical OpenGL initialization. The callback function's keyboard and mouse are for handling. User input interaction. And display is for managing window rendering. The init function configures a 2D projection with 600 × 500 window. The default point size is set to 3 and the default color is black. The function draw. Renders a single point on the screen. The function display clusters visualizes clustered data with the following styling. It sets the point size to 5. It displays points of cluster 0 with red, cluster 1 with green, cluster 2 with blue, and cluster 3 with black. Then it sets the point size to 9 and displays the cluster centers with the color magenta. At the end it restores the black color and the default point size 3. The callback function mouse triggers when a mouse button is clicked. If the left button is clicked, It calls draw dot to render a point at the mouse cursor's coordinates. The point is saved in the vector point vec using the vector member function pushback, which appends the point to the vector. The callback function keyboard handles key presses. When key K is pressed, do k-means, which performs k-means clustering, is called. When key D is pressed, it executes display clusters as discussed above. Below is an example of the graphical window displaying clustered data points and their centroids. Let's copy, compile and run these programs to observe their functionality in action.
Now let's copy these files. Let's copy the k-means.h first. So we copy it and we paste it. The k-means.h. Okay, and save it. And now let's copy this k-means.cpp. Okay, and paste it. Okay, so this is the file we copied, and we save it. Now let's compile this. So it compiles successfully. Okay, and we get this object file k-means.o. And now let's copy this testing k-means routine, test k-means.cpp. Okay, oh, sorry. So we copy this. And this will be a test k-means.cpp. So we've copied this. Okay, we could save it. Okay, and now let's compile this minus O, the executable, to be a test mean. We need to link it with the k-means.o. Okay, so it compiles, and now we can execute this. Okay, so you can see that it clustered the points into different cluster, free clusters 0, 1, and 2. Okay, so these the points here. Okay, and now if we try again, okay, the clusters could be different from what we had before. That's because we start with different centroids. Okay, so we randomly initialize centroids. Okay, so that's why we get different results. Okay, now let's try the graphical interfacing. So we are copying this file. Test k means sg.cpp. G means graphics here. So copy and paste it into this file g.cpp. Okay, so this is our file. Okay. Okay, so we save this. Now let's compile this. So it compiles. So we got this object file, and yeah, we could link this. -O, okay, to obtain the executable with well, the k-means object file, and also we need a link with the graphics library, -LGL, -LGLU, and cut OpenGL utility library. Okay. Enter. Okay. So we get this executable test k-mean sg. So we can execute this. Okay. So you can see that we get this window 600 by 500. Okay. And we can click on the screen at random positions, so to get some points. Okay. Okay. And now I press the key K, so you do the cluster called the k-means function. Okay, so it clusters the points into 3 clusters, 1, 0, 2. Okay, so this is the center of cluster 0, center 1, center 2, and now suppose I press the key D, then it shows the clusters using the colors red, green, blue, and the large dot in magenta are the centroids. Okay, so here center 0, the red, okay, is at 348, 341. Okay, this one, and then this is should be the cluster 1, the second one. Okay, at 141, 400. Okay, so we count from the bottom as 0, 0. Okay, so this is 141, 400. Okay, and then this is blue, the blue dots. Cluster center is at 198, 232. Okay, now suppose we add more dots. Some dots here. Okay, maybe some dots here. Okay. So now we have more than 15 points. So we have 4 clusters. Okay, so suppose I press the key K again. So you can see that indeed we have these clusters. Okay, 0, 1, 2, 3. Okay, corresponding to these points. Okay, and again, suppose I press D, then it shows the cluster points in red, green, blue. So this is red. Okay, for these points. Okay, the red, the center. Okay, is at 198, 232, 198, 232, and cluster 1, the green. Okay, that is at 362, 344. Okay, and the blue one, the cluster 2, okay, is 152. Okay, 394. So this the blue dots, the other cluster 2. Cluster 3 are the black dots. Okay, and the center is at 416, 182, 416, 182. This center. Okay, so these are the cluster center, and it makes sense, right? You can see these clusters. Okay, now you can add more dots. Okay. And press K. So we get these new clusters. Okay, and suppose I press D. So we again get these new clusters. Okay. So this wraps up our discussion on unsupervised learning. So feel free to try it out yourself. Thanks for watching and see you in the next video. Okay, bye.